Okay, let's go ahead and get started. I'm going to be on the pad for most of today, but we'll start on the computer so we can see the results for the question of the day. I gather that flying is a little more popular than invisibility. As I said, we're going to switch to the document camera. So let me try to make sure that we're looking at the same thing. So today I'm going to begin a new topic, which is binary trees. And this topic is the last major topic we're going to cover in the course. I'm not sure how you'll react to this, but a lot of people describe binary trees as having a certain elegance to them, a certain beauty to them that people really appreciate. They bring together a couple of things that we've talked about. So with linked lists, we had a linked structure that had a set of nodes in it, and binary trees have nodes as well. It's a linked structure, but we tended to write kind of long, tedious code for linked lists. For binary trees, we tend to use recursion, and so it's kind of combining those two ideas we've talked about, kind of the linked structure idea, the recursion idea. They kind of come together in binary trees because they're a linked structure that we tend to process in a recursive way. There will be 4 different questions on the final exam about binary trees because it's a major topic and we're hitting it in the latter part of the course. 2 of those will be programming questions, 2 will be non-programming questions. For the 2 programming questions, I give a 10-point question and a 20-point question. So the 10-point questions are all pretty similar that follow a certain pattern that we're going to discuss in today's lecture. And tomorrow in section, the TAs are going to be going over examples of what would be 10-point binary tree questions. Then Wednesday, we'll talk some more about more complicated code and the idea of changing the structure, so a little bit more than just traversing a structure. And then that will lead to Thursday's section where we look at a bunch of 20-point questions. And then there's going to be 2 more programming assignments this quarter, and both of them involve binary trees. Well, let's begin with some terminology. So I usually draw a tree that has ints in it, int values. So let's see, let me go ahead and put something here, and something here. So I mentioned the idea that, as with the linked lists, that these individual places where we store data, we will refer to as nodes. So this is a tree that's composed of various nodes. The terminology that we use, I think, is a little easier to understand if you realize that computer scientists view the world upside down. So like, this is the part of the tree that's in the ground, and then it kind of, expands from there. So what would we call the part of a tree that's in the ground? We would call that the root of the tree. And that's a bit of terminology that we use for this node at the top is a root node. And then in a tree, what are the things that kind of split off, in different directions? We would refer to those as branches of the tree. So we would describe this node 12 and this node 7 as being branch nodes because there's more structure that branches off, underneath those nodes. So we would consider those to be branch nodes. And then what's at the very ends of the branches, the tips of the branches on a tree, we refer to those as leaves. So this node here, this one here, and this one here, we would refer to as leaf nodes because they don't have any branching underneath them. They're kind of the end of the tree, the tip of the tree there. There's some other terminology that we use for this that we will sometimes talk about the idea of a parent-child relationship. So we would say that the root node here is the parent of these 2 nodes right here. These 2 nodes we might refer to as being siblings because they have the same parent. So this also leads to terminology where we can talk about, descendants of a tree, of a node, ancestors of a node. So there's often that kind of terminology that we use as well. All right. Normally I'd ask for questions, actually with these binary tree lectures, I get some interesting questions. So it's too bad that I'm not going to have that opportunity. But maybe in the Q&A, you guys will ask some interesting questions. But I wanted to then give you a definition that we can work with. So I'm going to say that a binary tree is either an empty tree, so that's one possibility, an empty tree. The other possibility is that it is a root node with left and right, left and right subtrees. So I am defining a tree in terms of trees. So this is a recursive definition that I'm using here. The left and the right subtrees are distinguishable. So in mathematics, when they talk about a tree structure like this, they would describe this as an ordered tree, because sometimes in mathematics, you don't worry about what's to the left versus what's to the right. But for our purposes, we're going to distinguish between the left and the right. And we'll see this starting in Wednesday's lecture, that it can matter what's on the left side and what's on the right side, that there's some meaning to that distinction. But I wanted to draw a little picture that I have in mind that I'm going to remind you about for this second definition here, the root node with left and right subtrees. I kind of have a mental model where I think about a root node. So there's some kind of a root node for a tree. And there is a left-hand subtree, and over here there is a right-hand subtree that I kind of draw as, little triangles. So when I'm thinking about a tree or reasoning about a tree, I find it very helpful to kind of have this picture in mind, where I'm thinking of, from the point of view of the root node, that there's something off to the left and something off to the right. But in general, I like to think of this as a tree. I kind of imagine that that's a tree itself, and that what's off to the right is a tree as well. So that's kind of an important way of thinking about it. Well, let's see what we can do using a definition like this. So suppose we want to think of some different kinds of tree structures that can be generated. So, the simplest kind of tree would be an empty tree. So I'm about to draw an empty tree. Get ready for it. 1, 2, 3, boom. I just drew an empty tree. Well, I don't know how to draw an empty tree. Maybe I'll just kind of put the word empty here to indicate that there isn't anything. But so there's a notion of an empty tree, nothingness. There are no nodes, there's no data in an empty tree. But since that's a possible kind of tree, having an empty tree, then we can use the second part of the definition to say that a new kind of tree would be a root node that have left and right subtrees that are empty trees. So I can have a node. I'm going to just put a little dot for the node. I'm not going to draw any actual data because I'm just thinking about the different kinds of structures. So I can have a node, and if its left-hand subtree is empty and its right-hand subtree is empty, then that would be a leaf node. That would be like these nodes right here. So these nodes I would still consider to be trees. It's just that they're trees that have empty left and right subtrees. So a leaf node is a tree. So an empty tree is a tree. A leaf node is a tree. And then I could have a node that, for example, now that a leaf node is a possibility, I could have the left and the right each be leaf nodes. So that's a new kind of tree. Or I could have the left tree be a leaf node and the right tree is empty. Or I could have the right-hand subtree be a leaf node while the left-hand subtree is empty. So these are all possible trees as well. And then once I have these possibilities, I can have something like, say, a root node here, and off to the left I have a leaf node, off to the right I have, say, that structure right there. So I can kind of pick this as being off to the right, I can pick this as being on the left. So all sorts of combinations that you can generate using that basic definition right here. So that's kind of a good definition to be coming back to as we think about what a tree is and how to kind of approach the tree. This recursive definition is going to be very helpful. When we did linked lists, I kind of talked about the idea of what would be the Lego building block, you know, kind of the basic unit that we would use to snap a bunch of them together. What does a node look like? And so let's talk about the equivalent for a binary tree. So in the case of a linked list node, it had two things in it, if you remember. It had a place to store some data. Well, there's a place to store some data in a binary tree node as well. And I'm going to do the same thing I've done with the other structures we've looked at, which is I'm going to assume simple int data for now. You know, for most of the examples we're going to look at, we're going to be looking at a tree that stores int data. But obviously we're going to do more interesting kinds of binary trees. On your homework, you're going to be looking at binary trees that store more interesting data than just simple ints. Now, in the case of the linked list, we had data and then we had a next. So there were just two things. But in the case of the binary tree, we have three things. So there's a link to the left-hand subtree and a link to the right-hand subtree. And so I'll kind of draw that as there could be an arrow here. I'll draw that as there could be an arrow here. So we branch in two different directions potentially, not just in the one direction the way that we did with linked lists. So that's what a node looks like. Let me show you some actual Java code. So this is what our int tree node class is going to look like. It has those three things. It has the data, which for now we're considering a simple int data, and it has left and right subtrees that we keep track of, a reference to, by keeping track of, by having int tree node fields for the left and for the right. So three different things inside each of our nodes. And then I have a couple of constructors here. This is a constructor for a leaf node that takes just some data and it doesn't take links for left and right. This would be a constructor for a branch node that takes all three. It takes the data and the link to the left and the link to the right, and it sets all three fields. Now here what I'm doing is I'm using that notation of this with parentheses. This, you know, something or other with the parentheses. And I mentioned this earlier in the quarter, that when you use the keyword this using the parentheses, that's understood to be one constructor calling another constructor. So what I'm doing here for the leaf node constructor is I'm calling the branch node constructor, but filling in null and null for the left and the right links. So we did this with linked lists. We're going to do it with binary trees as well, that the value null will be used to indicate an empty tree. So when we see null, we understand that to mean an empty tree. I mentioned earlier in the quarter that this is a style issue, that we want you to use the this notation as a way of eliminating redundancy. I don't want to have these lines of code repeated up here. So it's better to kind of have the one constructor. Everything gets funneled through this one constructor here, either directly or indirectly by the call on this. And we expect you to use that approach for your homework 7 and 8. So that's a style issue you're going to want to be paying attention to, is for your node classes, you want to be using the this notation as a way of eliminating redundancy, so that we basically have just the one real constructor that everything ends up calling one way or another. So that's what our nodes are going to look like. And you know, the public fields, again, that's a dangerous thing. We don't like that in general. But that's because what we're going to do is we're going to have a public class that I'm going to call int tree. And this is the class that a client is going to have access to, is the int tree class. And the int tree class will manipulate nodes, but we're going to make sure that a client of int tree never sees a node. So we're going to make sure that, just like we did with the linked list, that the node is going to be entirely on the implementation side of things. And so that's why we can be relaxed here and have these fields be public, because the client of the int tree is never going to see those node objects, is never going to have any danger of causing damage by having the public fields, because the client never sees them. So what do we have for fields? This usually leads to an interesting discussion when I ask people. I have to kind of fill in that for you. Well, there's a similar thing with binary trees as what we saw with linked lists. Remember that with a linked list, if we had access to the front of the list, that gave us access to everything in the list. Because starting from that node at the front, we could go next, 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 and we could kind of get to wherever we needed to get to be able to manipulate some part of the list. Well, there's a similar aspect to binary trees, which is that if we have access to the root, then we have access to everything. Because, well, obviously we can access the root itself, but then we can also access its children, and then if they have children, like the 7 node has children, then once we get to the 7 node, we can go left or right to access its children. So from the root, we can get to everything that's in the tree. Everything derives from the root one way or another. So what we can do is to have a field. So we'll have a private field. This one is going to be nicely encapsulated, of type int tree node. And I'm going to refer to this field as overall root. You might think of calling it root, but I'm going to explain a little later why I prefer to call it something slightly different than root. So I'm going to call it overall root. I ask people for suggestions for other kinds of fields, and people often have interesting and useful suggestions. I mean, like an obvious one is it would be nice to keep track of the size, to have some kind of an int field that would keep track of how many nodes there are in this tree. But I'm going to do the same thing that I did with linked lists, which is that I'm going to keep it really simple and just have this one field. So I'm going to say ... because what's left here then is filling in some public methods. Well, and in fact, size then becomes a problem to solve, is that you can make that a method that you guys will write by accessing the overall root and counting the number of nodes in the tree. So it becomes an exercise that actually is part of tomorrow's section. So it's one of the 10-point questions that we are going to be discussing in section tomorrow. So we're keeping it simple by having the overall root. I'm going to show you a nice version of this that does have a size field. So you really would want to include the size field so that you don't have to traverse the tree in order to find the size. But as I said, we're going to keep it simple. Okay, so that's what our tree structure is going to look like. The tree is interesting in that, ever since the beginning of the quarter, I've been talking about this idea of traversal, kind of traveling around a structure, visiting every element of the structure once. For example, printing it out. And we started by looking at linear structures like lists. And it was really obvious, how you traverse lists. You just kind of go from the beginning to the end. It's not at all obvious how to traverse a structure like this. When you have branching involved, what would be the order in which you do it? And I don't know, some people have a kind of a prejudice that we might go, layer by layer, like, do the 12 and then do the 18 and the 7 and then do the 4 and the 13, kind of, level by level by level. I mean, that's one thing you could do. There's all sorts of possibilities that you could do for a traversal. Well, let me tell you what we have in mind that we want you to know. And this is actually, it's an interesting thing. If you take a look at different CS2 courses, this is our second course in computer science here at the University of Washington. If you look at other universities' CS2 course, one of the almost universal things that you'll find there is that they ask students on their final exam to do binary tree traversals. This is like one of those most basic things that you always expect students to be able to do, is that there are different traversals that each have a name, and it makes for a great final exam question because it's really easy to grade. It's a very concrete thing. So we're going to want you to know about binary tree traversal. I mentioned to you that the final exam is going to have 4 questions on binary trees, 2 of which are programming questions. Well, one of the other 4 questions is a binary tree traversal question, where I give you a tree and I say, tell me the different traversals of a binary tree. All right, well, so what are the different traversals? How do we understand them? Well, there's some prejudices that I would say that we have. There's the idea of a left-hand subtree, the idea of a right-hand subtree, and I would say that there's kind of a Western bias that we have in all of this, that we do the left-hand subtree before we do the right-hand subtree. There's no reason to do that particularly, but in the West, we tend to read left to right. So there's kind of a prejudice, I think, that the traversals do the left-hand subtree before they do the right-hand subtree. There's a kind of a recursion prejudice involved in this, which is that when I'm going to do anything from the left-hand subtree, I want to do the left-hand subtree in its entirety. I don't want to be doing something from the left and something from the right. That's just not how we think of it recursively. So when I go to process things in the left-hand subtree, I want that to be the only thing I'm processing. It's kind of process everything from the left-hand subtree all by itself at some point in time. Process everything from the right-hand subtree all by itself at some point in time. Well, then, kind of what's left is that in our recursive definition, we talked about the idea that there's a root node that has left and right subtrees. So we know we're going to do the entire left-hand subtree by itself and do that before we do the entire right-hand subtree. The question is, where do we process the root? So like if we were going to print things out, when do we print the value that's stored at the root? Well, there's 3 possibilities, and normally I ask the class to tell me about the 3 possibilities, but you're not here, so I'll have to kind of answer for you. One possibility is that we kind of do it first, so that we do the root, we print out the root of the tree first, and then we process the left, and then we process the right. So that's kind of one approach, root, left, right. That's one traversal possibility, and that's known as a preorder traversal. So that leads to a particular traversal, preorder. Another possibility is that we process the root in between these 2. So another way to go would be to kind of have the root processed here. So instead of processing it first, we do left, root, right, so that we process the root in the middle relative to the left and the right. That's another possibility, and we refer to that as an inorder traversal. And then the final possibility, I'm sure you can see, is that we could process the root after we process the left and right subtrees. So let me see if I can kind of cover up the correct things. So we could do it in this way, where we do the left-hand subtree first, then we do the right-hand subtree, and then the root is the last thing that we end up doing, left, right, root. So that's another possibility, and that's referred to as a postorder traversal. So we want you to know all 3 of these traversals. There will be a final exam question where we show you a tree and we ask you to give the 3 different traversals of the tree. Well, I have a tree. I want us to kind of do that, to kind of do a traversal of this particular tree. I tend to do it this way, where I use the numbers 0 through 9, kind of single digits. So there's 10 of these things. And I ask you to show me, say, the preorder traversal of this tree, the inorder traversal, the postorder traversal. Well, let's do a couple of these. So let's do the preorder traversal. So in the preorder traversal, we have a root node that has 2 in it. There's its left-hand subtree, and there's its right-hand subtree. So in the preorder traversal, let's just assume that we were printing. We would print the 2 first in the preorder traversal, because we do the root first. Then, after we do the root, we do its left-hand subtree. So how do we process its left-hand subtree? It's got a 0 at its root, and we do the root of the tree first, so we would print out the 0. And then we do its left-hand subtree, and then we have this little 3-node little subtree. I think that I like thinking about the little 3-node tree as a way of thinking of these traversals in their more pure form, because this kind of looks like the picture I was drawing, where I have little triangles to the left and a triangle to the right. So, we know we're going to do 6 followed by 5. We do the left followed by the right. The only question is where the 7 is done relative to the 6 and the 5. So in the preorder traversal, the 7 comes first. So it would be 7, 6, 5. So I can put a 7, 6, 5 here. And so now we've done the root. We've done, in working on the left-hand subtree, we've done the left-hand subtree of this little subtree. Its right-hand subtree is empty, so there's nothing to print. So now we've finished the entire left-hand subtree of the overall tree, and we work on this tree. So we're going to do its root first, which is a 3. Then we want to do a preorder traversal of its left-hand subtree. So I usually ask the class, and by now people are able to say that would be a 1 followed by an 8. That's for the left-hand subtree of that little tree. Then we do the preorder traversal of the right-hand subtree. And people are usually able to say we do the 9 before the 4. So that would be our answer for the overall preorder traversal. Now let me point out something about this, which is that I've got a 2 right here, which was the overall value for the root. And then everything from here to here came from the left-hand subtree of the overall tree. And then everything here came from the right-hand subtree. So you can kind of see that rule, root, left, right. That was what I had talked about here when I talked about the idea of root, left, right. That's what we would do for the preorder traversal. And it's not just at this level, but it's at all levels. Like the right-hand subtree has its root followed by the 2 nodes from the left and the 2 nodes from the right. So this is also root, left, right. Kind of the little substructure of all of these things. So that would be a preorder traversal. How about an in-order traversal of this tree? Well, in doing the in-order traversal of the tree, we do an in-order traversal of the left-hand subtree first. And then we're going to do the root. So we're going to do this subtree first. And then in doing this subtree, we do its left-hand subtree first. So we're down to our kind of pure 3-node version of this thing, where the 6 always comes before the 5. It's just where the 7 goes. And in the in-order traversal, it's in the middle. So it's 6, 7, 5 is what I would have for kind of the traversal. 6, 7, 5 is the little traversal of this little tree here. That was the left-hand subtree of the node that had 0 in it. So now that we've done its left tree, we do the root, which is the 0, and then we do its right-hand subtree, which is empty. So that kind of completes the left-hand subtree of the overall tree. So now we're ready to do the root of the overall tree here. And then we do its right-hand subtree, which is this right here. We're going to do an in-order traversal of its left subtree. That gives us an 8 followed by a 1. And then we do the root itself of the right-hand subtree. And then we do an in-order traversal of the right-hand subtree, which gets us a 9 and a 4. So here you'll notice that I have the root value right here. And what's here is the left-hand subtree, data that came out of the overall left-hand subtree. And here, this is data that came out of the overall right-hand subtree. And you can see that, as I said, even within the structure, like within the right-hand subtree, the root node of the right-hand subtree is in the middle with its left-hand subtree's traversal here and its right-hand subtree's traversal here. So anyway, that's how we would do the in-order traversal. So this is something that the TAs might mention a little bit in section. I think this is something that you don't need a whole lot of help to study. I mean, practicing it, I think, helps. So I think that by the time the final rolls around, when students are actually graded, with a proctored exam, they're usually glad to have this question on the test because they can usually get a very high score on this just by practicing enough. Well, I want to mention a different idea about this, kind of a different way of looking at this, and it's something that I've always heard of as the sailboat approach. This is kind of a funny thing because I remember hearing about this many, many years ago in the 1980s, so somebody talking about this as the sailboat approach. But when I go to Google it, I actually don't find a lot of references to this as the sailboat approach, and most of those references point back to me. So I didn't invent it, somebody else invented it, but I think that we've kind of lost track of who invented it, and I've been one of the people keeping the idea alive. But the idea would be this. Think of these different nodes of the tree as being islands. And so kind of imagine that there's a solid wall, that's kind of preventing you from sailing kind of where you might want to otherwise because of these walls that are here. And we've got these different islands that exist. Imagine that a sailboat kind of comes in from this direction and it hugs the coastline. So it kind of travels along here, hugging the coastline. So it kind of always stays as close as it can to the coastline. Comes around here, hugging the coastline, under here, under here, under here, under here, under here, and then it comes all the way back out again on the other side. So that would be kind of the path that the sailboat would travel as it sailed around this set of islands. Now, think about a node like 2. How many times does the sailboat pass that node with the 2 in it? Well, it passes it once initially, on the left-hand side of the node, and then later, as it comes back around again, it passes underneath it. And then later, as the sailboat is leaving, it passes it one more time on the right-hand side. So what I would say is that for any one of these nodes, the sailboat passes it 3 different times. It passes it on the left, it passes it underneath, and it passes it on the right. So it passes it 3 different times. And if you kind of print the node as you're passing it on the left, you get a preorder traversal. If you print it as you're passing underneath, you get an inorder traversal. And if you print it as you're passing on the right, you get a postorder traversal. Now, some of these nodes, like this node with the 6 in it, you might say, well, it doesn't pass the node with the 6 in it 3 different times. It only is visiting that node once. Well, I would say it really does pass it all 3 of those different times. It's just that they all happen one right after the other. So it passes it on the left, then it passes underneath, then it passes it on the right. So those things can come right next to each other, the 3 different passes. But it still does do all 3 of the passes. It still passes it on the left, it passes it underneath, and it passes it on the right. So let me show you kind of how you would use this approach then to do the equivalent kind of thing. So let's think about the inorder traversal. So what is the first node that we pass under? Well, we're passing to the left, to the left, to the left, to the left, to the left. The first one we pass under is the node with 6 in it, and that was what we put here. And then the next node we pass under is the node with the 7 in it. Then we pass under the node with the 5 in it. And then we come around here and pass under the node with the 0 in it. We come around here and pass under the node with the 2 in it. And then we come back around this way and we pass under the node with the 8, under the node with the 1, under the node with the 3, under the node with the 9, and under the node with the 4. So that's another way of kind of coming up with the traversals. Some people think of this as a cheat. I think that in some ways it simplifies the problem, but I think it gives you another way of understanding what's going on that can be useful in its own way. This approach to things is a variation of something that's known as an Euler tour. That's supposed to be a U. Euler was a famous mathematician and had some interesting results in graph theory. And so it's kind of interesting. If you go to the Wikipedia page for binary tree traversals, you'll find some curious pictures. So there's a picture here. This is right from that page. I copied it from the Wikipedia page. What is that dashed line? What's this dashed line? And then even a little arrow here. Isn't that the sailboat? Isn't that the path that the sailboat follows? And it's showing you dots on the left-hand side. So it's kind of, of each of these nodes, and it labels that as a preorder traversal. This is the sailboat approach, where you're printing out the node as you pass it on the left. And they have a similar picture where they show the same sailboat going around, and they describe it as an in-order traversal, and the dots are underneath. It's when you pass it underneath. And they have a third version of that diagram that they label as a post-order traversal, where you process when you're passing it on the right-hand side. All the dots are on the right-hand side. But it's basically, I would say that they're doing the sailboat approach as well. Okay. This lecture's going a little faster than usual, because usually there's questions that slow me down, but I guess that's okay. It'll mean that I'll be able to show you a few things at the end that sometimes we don't have time for. I wanted to go back to that picture that we had before, this tree that we did the traversals of. I have a clean version of it here, and I want us to write some code. So I want us to write code that would do the different traversals. So we're going to consider the preorder traversal. We're going to write the code that does the preorder traversal. But before we get there, I want to ask a question. So the question I have is, look, I'm showing you a structure here. How many trees do you see? How many different trees do you see in that structure? And I get lots of different answers. One answer that I don't get very often, I get sometimes, but I think it's an interesting answer, is one. There's one tree. I mean, it's all connected. It all emanates from this root, so there's only one tree here. And that's a reasonable answer, actually. That's a defendable answer. There is one tree that's here. But remember that we describe trees recursively, and if we want to think about writing code recursively, we're going to want to be able to process subtrees, not just the entire tree, but also various little subtrees. Another answer that I often get is 10. So that's an answer that many people will give. And I think that where that answer comes from is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I think people are thinking that each one of these nodes is a tree, represents a tree. And that's a good way of thinking of things. It's true. Each one of these 10 nodes is the root of a subtree. That was what our recursive definition was, right? That any given node can serve as the root of a tree, and it's going to have underneath it potentially left and right subtrees. I have often got an answer that I don't quite understand for sure, but I think I know what it is. I've had people who say there's 6 trees. So that's kind of another answer that people will often give. And I think that where that comes from is that people are thinking that these 6 nodes are trees because they're branch nodes. They have something underneath them. So I think that the people who give the answer of 6 are not realizing that leaves are trees as well. So leaf nodes are trees. So that's why it's not just 6. All 10 of these nodes would qualify as trees. But 10 isn't the answer that I'm looking for either. So think about something like this node that has the 6 in it. It's a leaf node. I used to work with a program that was described as a binary tree playground. that was kind of a fun little program for students to use, an interactive program that let you build trees and pull trees apart and do various things with them. And in that program, they had a cute little way of indicating something in the drawing, which is that they put a little bud right here and a little bud right here, that what you might find on the branch of a tree, a little bud that looks like it could sprout into something more, that, you know, eventually something could grow from that bud. So a leaf node has empty left and right subtrees, but we do want to kind of realize that that's a place where a tree could grow, you know, to the left, and a tree could grow to the right. So this leaf node has two empty trees that it is the root node of. So, but those empty trees are trees. And so there's empty trees here as well, empty trees here, and empty trees here. So those are all trees that we want to think about. Are there any other empty trees? I ask people, and people will point out, well, there's an empty tree here. Anything else? There's an empty tree over here, and there's an empty tree here. So there are several of these nodes that have empty trees. Well, how many of these are there total? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So there are 10 trees that are nodes and 11 trees that are empty. So the answer that I would give is that I would say that there are 21 trees. That's kind of the right way of thinking of how many trees there are here. And in terms of the code that we're going to write, I want us to write a recursive method that's going to be called 21 times, once for each of these little subtrees. Trees also have interesting mathematical properties to them. In fact, I can give you a mathematical argument for why the answer would turn out to be 21. Our recursive definition said that you know, the second part was that it was a root node with left and right subtrees. So every root node produces 2 subtrees. So if there are n root nodes, there will be 2n subtrees that are generated total. So every root node has the 2 subtrees, so that makes a total of 2n, and there's 1 overall tree. So there are 2n plus 1, we would expect 2n plus 1 total trees with a structure like this. There were 10 nodes here, so we had 21. If there were 15 nodes here, we would expect to see 31 trees. So that's kind of it's a nice mathematical property. Those of you who are math-oriented might enjoy that aspect of this. All right, well, let's write some code. What I want to do then is I want to make a public void method that I'm going to call print preorder. And I'm imagining that this is a method of the int tree class. So it's going to, where was that? Way back here. It's going to go in here. There's going to be a public method called print preorder that'll be included in the int tree class. Okay, how do we write it? I usually pause for a little bit to let people think about it. How do we solve this problem? There's a good aspect of kind of waiting a little bit and making you think, because what you should be realizing is, I don't see how it can be done. I mean, I don't see how, with a method that looks like this, that has no parameters to it, how does this solve the problem? How can I get this to solve the problem? You know, the idea, I said, is that we want to be able to have a method that we call 21 times with each of the 21 trees in this structure here. Well, this method doesn't have any parameters to it. Well, so this is one of those cases where we're going to have a public-private pair. And let me mention something that could be worth writing down or taking note of. Every interesting binary tree problem we will ask you to solve for the homework and for exams, every single one of them will involve a public-private pair. So you're always going to be using this technique, print preorder, And in particular, what I want to be able to do in this case is I want to be able to specify which of the 21 trees do I want to print. Well, I know that that nodes are used, the int tree node is the type that's used for keeping track of references to these nodes. So I'm going to say int tree node root. I want to have a version of this method where I can specify the root. And I mentioned to you that often the key to getting a recursive definition right is coming up with the correct parameter passing. So we're going to have kind of a call in here where we're going to call print preorder. We're going to get the whole thing started by passing it what do we know of in our class? Well, remember that in the int tree class we have something called overall root that's keeping track of a reference to what's at the top. So I'm going to start this whole process going by passing in a reference to overall root as the thing that I pass as a parameter for the initial root that I use here. So this parameter named root I'm going to use to refer to all 21 of the different subtrees here, including the empty trees. That's why I like to use a different name for the fields, a slightly different name. There's only one overall root, but we often write code like this that involves a parameter that we would call root that's a more generic kind of thing that could refer to any of these. Well, what are the easiest trees to print? You know, people sometimes say leaf nodes, and leaf nodes are pretty easy to print, but even easier than leaf node is all the 11 empty trees. If they're empty trees, there's nothing to do. So I could say if it's an empty tree and then have no code, but I'm going to do the thing where I say if it's not an empty tree, then we're going to say what to do in that case, and there's going to be an implied else there's nothing to do. So I'm going to say if the root is not equal to null, then what I want to do is that would be my recursive case, where I've got a root node with left and right subtrees. Well, in a preorder traversal, what's the first thing that I do? I process the root. So I'm going to want to do a system.out.print, of the data at the root. And what I have in mind is that I'm going to have a little system.out.print here. I'm going to have some code that gets executed once before the recursion begins. I'm going to print out preorder with a colon. That'll get printed out once. Then I'm going to print a whole lot of data here. And then after the recursion, I'm going to complete the line of output with system.out.println. You may remember that I mentioned that this is one of the nice advantages of the public-private pair. If there are things you want to do once, either before or after the recursion, then that's a nice thing, easy thing to do in this form where you have it in the public method. In the private method here, I'm using the same name, print preorder, but remember this has a parameter and this does not, so it can tell the difference between the one argument version versus the 0 argument version. But some people like to use a name like print preorder helper or preorder helper. That would be fine. But here I'm going to want to print, say, a space plus root.data. I'm going to want to print out the data that's in this particular root. And then what? Well, then you might imagine that once I print, say, the 2, then I want to see that that's not null, so I print it. That's not null, so I print it. That's not null, so I print it. That's that, rabbit hole, bad, non-recursive thinking. What I want to be thinking about is, look, I've got a root node that has a left-hand subtree and a right-hand subtree. And each of these subtrees has fewer nodes than the original because it doesn't include the root node. So that means they're simpler trees. So that means that I can kind of apply the leap of faith to know that a recursive call is going to work. So if only I had a method that would print in a preorder way a certain tree, I could ask it to do that with the left and to do that with the right. So I could say, please print in a preorder way my root.left, and let me print in a preorder way, my root.right. So I would print my left and right subtrees in a preorder way. and then I'd be done. And that, in fact, is the entire print pre-order code. I often ask people then, how do we change this to do in order and post order? If you put the printing command in between the two calls, you get in order. If you put it after, you have post order. I think we're about to get cut off. So the notes for today will say a little bit more about all of this, but I'm going to post a version of it that has all of this code in it with some extra code that I discuss in the notes. The key thing to understand, though, is this code here that will be on the calendar and in the notes for today, and we'll follow up in section tomorrow by doing similar kinds of